So we started looking at what's out there. There's a wireless sensor node that we've been working on. On the other end of the spectrum, there's RFID tags, like the Hitachi tags that are really tiny, a couple hundred micron on the side, thinned down to tens of microns thick. So these tags are really small. They've demonstrated operation without an external antenna. So, much smaller than 1 cubic millimeter for a tag. But of course, there's a power trade-off, there's a feature, functionality trade-off, and a huge flexibility trade-off as well. So the WISP really, in some ways, was sort of the best of both worlds. We have a really flexible structure that doesn't require huge batteries. In the work that we'll talk about today, we wanted to see if we could, go a step further and have, again, the best of both worlds, trying to shrink some of the functionality of the WISP down to a single chip. And so the application area that we're interested in are sort of biosignal interfaces. And there's a lot of different applications of this. We have some collaborators at Washington, people who are trying to record brain signals from small animals like mice and even insects. For a lot of reasons, they don't like these wires that are currently connecting the mouse head to a rack of instrumentation. So the wires are sort of frail. The mice like to chew on them. And when the mice move around, of course, the intention is that they collect data while the mouse is moving. The movement artifacts corrupt the data. So we need to get rid of all the wires and have something that is really tiny and doesn't have huge batteries that's sitting on top of the mouse brain. Of course, the noise levels that we're dealing with here need to be very, very small. So relatively precise electronics need to be incorporated in this form factor. So I'll talk about two different chips that we developed to do this on two ends of the spectrum. One is an active tag using an active radio with no RFID reader. This is work that we presented at ISSCC last year. So the architecture looks like this. We have low noise analog circuits on the left to hook up to brain electrodes or surface EMG electrodes and things like that. We have some logic on board to packetize the data. We have a FSK transmitter that operates in the 400 megahertz medical implant communication service band, and some external quartz crystals as a frequency reference. So we took a lot of effort to make sure the power dissipation of the system was very low to avoid those huge, 30 milliwatt power transients that we saw before. So this chip works. The total power dissipation is less than a half milliwatt with the transmitter on and with all the amplifiers on. So we were pretty encouraged by these results. And so our first application of this chip will be for remote therapy for children with cerebral palsy. This will be self-contained electrodes that are active that a child will put on their arms of their affected arm. And they would be able to basically control a computer game using this technology, and physicians would be able to monitor their progress remotely. So it's interesting project, and the technology works pretty well. We can power the chip with a 0.2 gram hearing aid battery for over 24 hours. And here's some traces that we measured a couple days ago. This is a person moving their arm. This is recorded EMG that's transmitted over a couple of meters to a receiver that reconstructs the signal in real time. Okay, so that's fine. But what we'd really like to do is completely eliminate the battery. And this is where we turn to your community for help. How can we design robust systems that are completely battery-free? The goal here was to utilize a very asymmetric link. We have power to spare on the reader side of things. So let's blast a lot of power at the tag, hopefully power it up, and hopefully not corrupt the very small signals that we're trying to record on the surface of the skin or on the surface of the brain. Dan Yeager was the lead designer on this chip. His goal was complete Gen 2 RFID compatibility. So I'll very quickly go through this. I'm not going to talk about the details. This will be presented in a couple months at ISSCC. But to get this chip working, you need a lot of different parts. You need a lot of logic, low noise front-end circuitry, some RF components, and a lot of regulation. Random number generator, unique ID generator, etc. All of this needs to go on chip in a completely standard CMOS process. So I'll talk about just a few of the highlights very, very briefly. We also need a relatively stable clock source without using a quartz resonator. So the Gen 2 protocol is relatively complicated. Dan did a good job prototyping this on an FPGA, making sure it works before mapping it to silicon. The chip ID generator comes from some work that we did a couple years ago, trying to extract a very stable chip ID from process variation on chip. Kevin talked about this earlier, where this looks a lot like an SRAM cell, where it will boot up into a random state, a state that looks random, but most of the bits will actually fire up the same over the course of time. So you can use it to generate a chip identification number. We have a means of temperature compensating an oscillator. So we have a stable 3 megahertz oscillator on chip. We also need low power, very low noise analog front ends. So a student, Fan Zhang, worked on a chopper stabilized amplifier that basically moves the input signal up into a band that has less noise. We need to have an efficient rectifier, and so Dan did some work on the rectifier that uses zero VT devices, so MOSFETs in our process that had very low threshold voltages to get a very good rectifier efficiency. Okay, the symbol tag looks like this. There are, on the right of the chip, there's a chopper amplifier. This is about 1 by 2.5 millimeters. The rest of the tag, the logic, ADC, ID generator, random number generator, is on the left side of the tag. He put 2 versions down. One of them is meant to interface to an MSP430 to give us additional flexibility. And we still need a few external components for one of the deployments that we did. So we made a small PCB that's a little less than a centimeter on a side. So our goal is to make a wirelessly powered temp sensor, something that will give us accurate remote reporting of a temperature in a mass that's less than about 350 milligrams or so. So no battery. Including the antenna and including a thermocouple, which is used as a temp sensor. The range that we reported was about 2 meters using an impinged reader with an alien tag. Okay, so here's actual temperature versus ADC output code measured wirelessly, and it looks fairly clean. This is a graphical user interface. Dan might talk a little bit about this during the tutorial later, or at least how these are designed. We have ability to change the averaging, and we can read out the temperature in real time through a PC. So what do we do with a really small temp sensor? We have a collaborator in the biology department who is interested in studying the thermal gradients across the DLM, across the big flight muscles in a moth. And we realized that with this platform, she can have access to data that no other biologist has access to. The temperature in these flight muscles while the moth is in flight, completely untethered. And so that was the first step with this chip, is to try to deploy this on a moth while it is flying. So here's what the system looks like. There's a small white PCB, a thermocouple, which is just 2 dissimilar metals with the ends twisted together, that is implanted into the moth with a little bit of wax to keep it fixed in the muscle. 900 megahertz dipole, which looks familiar to WISP users. And in the background, you can see the tag reader. So here's what it looks like while the moth is flapping its wings. So the moth starts out essentially at room temperature, and it has to warm up before it starts flying. So it goes through a period of shivering, where the temperature will start to rise. And then when the moth finally starts flapping its wings, the core body temperature, the muscle temperature, will rise from room temperature up to around 40 degrees C or so. So you see a huge difference in temperature as this moth starts flying. So we're pretty excited about this demo and also other things we can do with this technology. Okay, so just to wrap things up, we saw that earlier today, Josh made a really good case that Moore's law is necessary. It is necessary to do what we're talking about in this room today, but it's definitely not sufficient. There are a lot of other challenges on the analog side and on the RFIC side to make these WISPs actually have a really big impact. The second observation is that IC designers, of course I'm a little bit biased here, but IC designers can have a tremendous impact on healthcare and implantable devices. And this is really exciting for a lot of students coming into EE and CSC programs to see that this fundamental work they do on these little chips can actually really help people in the long run. And the third thing is, in my opinion, one of the next great challenges is trying to miniaturize these systems in every possible sense, not just the chip itself, but the batteries, the antennas, the solar cells, the sensors. And that will really enable a lot of interesting systems. Okay, thank you very much.
Thank you. Do we have any questions?
Do you have actual temperature data from the moth already?
We do have temperature profiles from the moth. I won't show them today, but they do look like what you would expect, a nice exponential rise in temperature on the order of 10 degrees C or so as the moth starts warming up. So it's pretty interesting.